The void is, without a doubt, one of the most enigmatic and fascinating concepts in physics. At first glance, we might think we know what it is. A space devoid of matter, empty, where nothing exists. However, reality is far more complex than it may initially appear. Modern physics, particularly through quantum mechanics and general relativity, has shown us that the void possesses extraordinary and counterintuitive characteristics, making it not just a subject of theoretical study but also a key to understanding the fundamental mechanisms governing our universe. Among the most mysterious properties of the void is its intrinsic energy, a characteristic that makes it a crucial topic in the study of the cosmos's evolution. But what is meant by vacuum energy? Where does it come from, and what consequences does it have for the expansion of the universe? Let us delve deeper into these questions, starting with the distinction between the philosophical concept of nothingness and the physical concept of the void. Can we truly imagine absolute nothingness, the total absence of everything? This question leads us to a paradox. Even by thinking about nothingness, we are attributing a form, an idea, or a concept to something that, by definition, should lack any properties. In physics, however, the term nothingness is never used in an absolute sense. Instead, the focus is on the void, understood as what remains in a region of space after all observable forms of matter and energy are removed. But can we truly achieve a state of absolute emptiness? Classical physics suggests that we can. By imagining the removal of every atom, every particle from a given region, we could theoretically obtain a perfect void. However, modern physics demonstrates that the void is never truly empty. Two major theories of physics, general relativity and quantum mechanics, pose fundamental challenges to the classical conception of the void. Einstein's relativity teaches us that matter and energy are two sides of the same coin. To create an absolute vacuum, it is not enough to eliminate all material particles. One must also remove any form of energy, including electromagnetic radiation. However, as long as a system's temperature does not reach absolute zero Kelvin, there is always a residual amount of energy in the form of thermal radiation. Consequently, even after removing every particle with mass, massless particles like photons, which carry energy, would still populate the void. Quantum mechanics introduces an even deeper complication. Heisenberg's uncertainty principle states that it is impossible to precisely know both the energy and the time in a given region of space. This implies that even in the perfect vacuum, there are energy fluctuations that can generate pairs of virtual particles and antiparticles. These virtual particles exist only for extremely brief moments, borrowing energy from the vacuum itself, as allowed by the laws of quantum physics. Essentially, no matter how much we strive, absolute emptiness is physically unattainable. Even under the most extreme conditions, the void remains a bubbling field of quantum activity. How can we prove the existence of these quantum fluctuations? In 1948, Hendrik Casimir proposed a theoretical experiment to observe the effects of the quantum vacuum. He imagined two parallel metal plates placed very close to each other in an almost perfect vacuum. Quantum mechanics predicts that only certain electromagnetic waves can exist between the two plates, while fluctuations of all frequencies are present outside. This difference creates an attractive force between the plates, now known as the Casimir effect. Subsequent experiments, such as those conducted by Steve Lamoureux in the 1990s, confirmed the reality of the Casimir effect, demonstrating that the void is far from empty but instead a sea of constantly fluctuating virtual particles. In modern physics, the void represents the minimum energy state of a system. Even after eliminating all observable matter and energy, a base energy intrinsic to the void itself would remain. While this energy is real, it cannot be harnessed. There is no lower state from which it can be extracted. Although it lacks immediate practical applications, vacuum energy plays a crucial role on a cosmological scale. Its presence is associated with the so-called cosmological constant, a quantity introduced by Einstein to describe the gravitational effects of the void. Astronomical studies, such as those conducted in 1998, have shown that the universe's expansion is accelerating, a phenomenon attributed to vacuum energy. A similar role might have been played during the earliest moments of the universe's life, during a period known as cosmic inflation. According to this theory, an enormous amount of vacuum energy caused a rapid expansion of space, laying the groundwork for the structure of the current universe. Despite significant progress, the value of vacuum energy remains one of the greatest challenges in theoretical physics. Observations indicate that its value is extremely small, while theoretical predictions estimate it to be vastly larger, with a discrepancy of 120 orders of magnitude. This gap suggests a fundamental lack of understanding of the interactions between quantum mechanics and gravity. Is the void truly constant everywhere, or could it vary over time and space? Could it conceal clues to new physical laws? The study of the void is not merely a theoretical exercise. It is a window into the fundamental laws of the universe. Solving the mysteries of vacuum energy could lead to a revolution in our understanding of physics, revealing new connections between the principles that govern the cosmos. Paradoxically, the void might hold the answers to the deepest questions about the nature of reality. Thank you for watching. Leave a like, subscribe to the channel, and activate the notification bell to stay updated on upcoming videos.